Okay, Anatomy 2 folks, so here is a little bit of a presentation from the Chapter 23 PowerPoint on respiratory system. We're beginning at about slide 72, and we'll see how long we go. I try not to make these videos too long, but just kind of follow along in your PowerPoint. So this is beyond all of the anatomy section of the chapter, which hopefully you've already been reading. And now we're talking about the process of respiration. So respiration actually encompasses two separate processes. There's external respiration, which has to do with the interaction between the air from outside the body and the lung. And then there's internal respiration, which is what happens within the cell. So external respiration is everything that's exchanging oxygen and CO2 and between the capillary and lung interface. And internal respiration is happening out in the body where we're taking in oxygen by cells and putting out CO2 by cells. And it's going to be the result of cellular respiration. Okay, so external respiration. Well, in order to have that happen, we actually have to breathe. That's called pulmonary ventilation. And then when we breathe, a small percentage of the gas makes it down into the alveoli, and there we're going to have gas diffusion. So it's going to have to go from the air pocket in the alveolus, through the wall of the alveolus, through the basement membrane that's shared between the alveolus and the pulmonary capillary, through the capillary wall, and make it into the lumen, into the bloodstream. So the gas diffusion first has to go from across the blood-air barrier in the lungs. And then to deliver that oxygen, we have to go out into the systemic circulation, and it's going to have to go across the capillary wall into the interstitial fluid and then enter the cells from there. Transport of oxygen and CO2 has to happen between alveolar capillaries and between capillary beds and other tissues. So again, respiration consists of pulmonary ventilation, and that's the physical bringing in of the different gases and the exchange that happens in the lung alveoli area. Pulmonary ventilation is breathing. It's the physical movement of the air. Now, we might think that we suck the air in, but actually it's a very different story. When we have our thoracic cavity formed by our chest, our intercostal muscles, and our diaphragm, it is of a certain volume. And then there's a certain amount of pressure within that chamber, within that thoracic cavity, and particularly within your two pleural cavities of your lungs. Now, there's also atmospheric pressure. Atmospheric pressure is the pressure of the air outside of your body. Okay, so it's the weight of the Earth's atmosphere is how the text defines it. Now, we need to understand some laws about gases and how they behave. So here's a visual. So the blue box represents an entire area of gas. And each of the little individual black dots represents a molecule of whichever gas. Let's call it oxygen right now. So those are individual oxygen molecules. And as long as they have the space in the blue box, they have a certain amount of pressure that they're exerting on the walls of the blue box because of their collisions with each other. If we squish them down into the area of the red box, well, then we're going to be forcing them to have the same number of collisions, but within a smaller space. They're going to be hitting the walls more often. We're actually going to increase the occurrence of collision because we've reduced the amount of space that they can move around in. So if we take a larger space and make it smaller, we increase the pressure of the molecules of gas within that new space. Okay? And if we do the opposite, we give it more room, well, that spreads the molecules out. So that lowers the number of collisions and lowers the pressure that those molecules are exerting by bouncing off the walls. So if we make a vessel that's holding a gas smaller, the pressure goes up. And if we make a vessel that's holding a gas larger, the pressure goes down. So let's talk about what's going on with our lungs. Air follows like any other gradient. It goes from an area of higher pressure to an area of lower pressure. And so in the process of changing the volume of the thoracic and pleural cavities, we are going to be influencing the pressure of the gases within those cavities. So a respiratory cycle, a whole cycle, consists of an inspiration, also known as an inhalation, and an expiration or an exhalation. So you inhale and then you exhale. Now, what you're doing is you're actually going to be constricting muscles that are going to increase the size of your chest cavity. That's going to be the physical pulmonary ventilation. And we're going to cause that area inside your chest to get bigger. And when we make that area bigger, well, as we just saw from those laws of the gases, that's going to drop the pressure inside the chest. Now, nature abhors a vacuum. And so the atmospheric pressure at that point is going to be higher than the pressure inside the chest. And so you don't actually suck air in. It forces its way in through your nose and mouth in order to equalize the pressure inside your chest and outside of your body. So what we're going to be doing in pulmonary ventilation is we're going to change the volume of the thoracic cavity by depressing the diaphragm muscle and flattening it out, and by using our external intercostal muscles to expand the rib cage. So when you inhale, you're going to elevate your ribs and sternum, and you're going to contract your diaphragm. So it's going to increase the space in the thoracic cavity. Again, increased space means a drop in pressure, and the atmospheric pressure will be higher. Therefore, the molecules from the atmosphere will force their way into your chest to try to equalize the pressure. You can kind of think of it as diffusion of air molecules instead, though we just call it gas pressure. Okay, and so at rest, our diaphragm is like an upside down bowl. It's very rounded, and our rib cage is in the depressed position. And the pressure inside and outside the lung is equal, and no air movement occurs. When we inhale, we contract our intercostal muscles, specifically our external intercostals, and we depress our diaphragm. Those are our primary respiratory muscles. Now, this is for our normal relaxed breathing. And inhaling is always active. Exhaling can be active or passive, but inhaling is always active. Now, we can just do a relaxed breath and only use our external intercostal muscles and our diaphragm. And that's just a normal inhale. Or you can forcibly inhale. Now, when you want to make the chest cavity even bigger and forcibly inhale, then you're going to recruit some more muscles, your accessory respiratory muscles, known as your sternocleidomastoid, your scalenes, and your pectoralis minor, and your serratus anterior. So that's going to increase the volume of the chest even more to give more room for more gas to come in. When we exhale, if we just took a normal breath, we simply allow the exhale to happen by relaxing the external intercostals and allowing the diaphragm to return to its rounded state. So exhaling is usually passive if you're in a relaxed state. But as you know, you could also forcibly blow air out. And so then you would recruit the accessory respiratory muscles of transversus thoracis, the internal intercostal muscles, and rectus abdominis. So those would give us a forcible exhale. So your primary respiratory muscles are the diaphragm and external intercostals. And then if you want to take in more, you will use your accessory respiratory muscles. The mechanics of breathing: inhalation is always active, and exhalation, as I said, can be either active by recruiting more muscles or passive by simply letting your primary respiratory muscles of inhalation relax. So in inhalation, the diaphragm contraction draws air down into your lungs, and about 75% of air movement is actually due to movement of the diaphragm. The little bit left, the extra 25% left over, is by the external intercostals. And if you think about it, the diaphragm can flatten itself and create a much larger space than just expansion by the external intercostal muscles would do. To exhale, if you're forcibly exhaling, you can use your internal intercostal muscles, which push the ribs back down. And then your rectus abdominis compresses the abdomen and pushes the diaphragm back up. Okay, so here's a little summary of those. Okay, so I said, your normal relaxed breathing or your forced inhale, forced exhale. We're talking about these two classes of movements. Quiet breathing. Quiet breathing would be a very gentle inhale and then simply allowing those muscles to relax for the exhale. So a passive exhale. Forced breathing is also called hyperpnea, and that's when you are actively inhaling and actively exhaling. And this is going to be using all of those respiratory accessory muscles. So, quiet breathing is called eupnea, active inhalation and passive exhalation. Now, you can add to that diaphragmatic breathing or deep breathing. Now, I'm a singer, so I've been learning how to use deep breathing forever. That's when you take your diaphragm and you compress it even more. So diaphragmatic breathing is when you primarily rely on the diaphragm for increasing the chest cavity diameter. Costal breathing or shallow breathing is usually only using the external intercostals. Now, when you relax after an inhalation, then all of the elastic parts that are connecting your muscles to your ribs, they are going to recoil. And so that's why we're able to exhale passively. So once we've contracted the muscle, once we let it relax, everything kind of just collapses back into place. And that would be our passive exhale. Now, the pressure changes. What's actually happening? So we can measure these changes either inside or outside the lungs. The normal atmospheric pressure is described as 1 atmosphere, which is 760 millimeters of mercury. Now, notice you have your lungs inside pleural cavities, an individual pleural cavity for each lung. So there's inside between the visceral pleura on the surface of the lung and the parietal pleura on the wall of the cavity, there's a space. That's our pleural cavity. Now, there is also an air pressure there. It's called the intrapleural pressure. Inside the lungs, we have pressure inside the alveoli, and that is our IntraPulmonary pressure. So we have the pressure inside the lungs where the air is actually exchanging, and then we're going to have a different pressure outside the lung between the lung and the wall of the pleural cavity. So let's first talk about intrapulmonary pressure. So this is the one that's going to be changing rapidly because when we increase the size of the thoracic cavity, this is where the air is going to go that forces its way in. So the bigger the difference between the volume of the cavity and the atmospheric pressure, the faster that atmospheric pressure is going to come in. In relaxed breathing, believe it or not, the pressure differential is actually pretty small. We have a change of about 1 millimeter of mercury on inhalation, and then we go up about 1 millimeter of mercury on exhalation. If you are breathing at your maximum capacity, however, forcibly inhaling and forcibly exhaling, you can swing it to negative 30 millimeters of mercury while you inhale, and it will go all the way up to positive 100 millimeters of mercury when you're straining, like if you're lifting a weight and you have your voice box, your glottis closed. Now, intrapleural pressure was that other pressure. So it's outside of the alveoli of the lungs, outside of the lung itself, but it's still within the sac, the pleural cavity. And it's negative 4 millimeters of mercury. Now, this makes a lot of sense. We want the lung alveoli to be held open and pulled towards the wall of the thoracic wall, okay? So that keeps the lungs inflated. Now, if you take a huge inhalation, that can actually go down to negative 18 millimeters of mercury. So if we always have our intrapleural pressure below atmospheric pressure and even below intrapulmonary pressure, that keeps our lungs inflated. Cyclical changes in the intrapleural pressure create a respiratory pump, and this squeezing also helps return venous blood that is in the lung and lung area over to the heart. So what's a pneumothorax or a collapsed lung? That is what happens if air gets into the pleural cavity. So now, instead of being at negative 4 millimeters of mercury, which holds the lung open, atmospheric pressure enters and goes to the outside of the lung. And since atmospheric pressure is 1 atmosphere or 760 millimeters of mercury, it's going to push the lungs and crush them. It's going to collapse the lung and push air out of the alveoli. It results in a condition called atelectasis. That's a collapsed lung. So in order to solve a pneumothorax, we actually have to suck air out of the pleural cavity and seal it back up so we can return the lung to its fully inflated position. So respiratory rates and volumes. Your body is going to be monitoring oxygen demands and oxygen levels and CO2 levels, and it can respond by changing either the number of breaths you take per minute, that of course would be your respiratory rate, or how deep you're breathing, the amount of air moved per breath, which is your tidal volume. So your respiratory minute volume is the amount of air you move per minute. So that's the number of breaths per minute times the volume of air per breath. And that's your normal pulmonary ventilation. So you can see here our pressure changes. Some inhaled air gets all the way down to the surfaces of the alveoli and gets to do the exchange. But guess what? Anything that's not in an alveolus has to enter and leave, but it doesn't actually contribute any oxygen. So that is called the anatomic dead space. So everything in the bronchioles, the bronchi, the trachea, the pharynx, the nasal passages, even in the mouth, all of that air is basically wasted air with each breath. So alveolar ventilation is the amount of air that's actually reaching the alveoli each minute. And that's your breathing rate times your tidal volume, the normal amount of air you're pushing in and out, minus all of that air that's in the anatomic dead space. Alveoli will always have less oxygen than atmospheric air because every time you breathe in and out, actually we don't completely replace the air in the alveoli, and new oxygenated air mixes with old used air. So how do we measure what's actually happening in a person's body, their respiratory performance? Well, we use a spirometer. And a spirometer is something that we're able to blow in and look at forced air in, forced air out, and things like that. So some important terms to learn are tidal volume. That's a regular relaxed breath, the amount of air that gets moved in and out of your lungs. Now, after you have exhaled, you can always blow out a certain additional amount. That's called your expiratory reserve volume. Now, there's going to be some amount of air that can never be exhaled. That holds the alveoli open and doesn't let them close in on themselves. And so that is called your residual volume. And then after you've taken a regular inhale, there's also a certain amount of air that you can suck in after that. So if I did a regular inhale and then I go and I take in as much as I can take in, that would be my inspiratory or inspiratory reserve volume. So your inspiratory capacity is your regular breathing volume plus your inspiratory reserve volume. So that's basically your regular inhale plus your biggest inhale that you can do on top of it. Your functional residual capacity is your expiratory reserve volume plus your residual volume. Your vital capacity is everything that can actually move in and out of your lungs. So your expiratory reserve volume, your regular tidal volume, and your inspiratory reserve volume. So think about it. If you pushed out as much air as you could, took the largest breath in that you could, and then pushed out as much air as you could again, that would be your vital capacity. So your total lung capacity is your vital capacity plus your residual volume. All right, so here's some examples of some pulmonary volumes and capacities. I think that is enough for this lesson. I will talk to you and make another video soon.